Okay, so I will be explaining the introduction and the results. So first we see how structured light act like messenger of quantum truth. So first of all, we will see what is structured light. So let's consider a light which has certain special property like amplitude, phase, and polarization, which are engineered in a continuous way and can make a structured light. Okay, we don't need to write that. Okay, fine. So uh, we can also see if there is a laser, and a laser beam is typically a Gaussian light, a Gaussian beam. We can we can have we can have vertex light from it. We can have vortex beam, vector beam, or more complex spatial structures, which are helped to explain the quantum mechanical phenomenon. Okay, and it is important because the structure light act as a classical analog of certain quantum system and can mimic complex quantum behavior. Okay, and these quantum complex behavior are like complex behavior like entanglement, superposition, and squeezing. So our main focus is in squeezing. So these can be achieved only by using classical light. This behavior can be studied using classical light. Classical light. Okay. So before we jump into quantum squeezing, let's see what is discrete variable and continuous variable. Okay. Discrete variable and continuous variable quantum systems, basically quantum systems. So first, in discrete variable, it is basically a finite dimensional like spin up and spin down, which forms the basis. Okay, and these maps these maps will to the discrete spatial or polarization mode in classical optics, whereas the continuous variable, which is an infinite dimensional Hilbert space, like position and momentum. They support phenomenon like quantum squeezing, for which actually we are here. So these continuous variable actually help us to explain the quantum squeezing. Okay. So now let's see what is quantum squeezing. Okay, in quantum optics, let's consider a vacuum state, which is represented as a circular globe. Circular globe. These two axes are basically quadratures Q1, Q2. Here is my vacuum state. Uh, it is in phase space and have equal uncertainty in both the quadratures Q1 and Q2, which is basically 1 by 4 and 1 by 4, and their product will be 1 by 16. This uncertainty is called SQL, or standard quantum limit. Similarly, in classically, a light can focus at a minimum point, which is also known as, that limitation is known as SSL, standard spatial limit. Okay, so here is my vacuum state. Vacuum state. So by the addition of photon, by the addition of photon, we are giving some energy and we are squeezing in one of the quadratures. Let's say Q1. Okay, so we squeeze the uncertainty in one direction in Q1 and we increase the uncertainty in Q2. So these are our squeezed state. Fine. As we understood quantum squeeze light, let's look into the classical analog. So in classical analog, we make squeeze light with structured light. So basically what happen is, we have a laser, we get a light which is let have a Gaussian beam. Think of it as a classical vacuum, okay, and add higher order modes. Higher order modes of what? Higher order modes of uh, HG modes, basically Hermite uh, Gaussian modes, which will be discussed later. And similar, this higher order modes are similar to that of addition of energy or photons. So we get a classical squeezed light field. Okay. So what happened in classical squeezed light field? Here, it becomes tight in one axis, but expand in the another axis of the Fourier plane. Like if here the squeeze is in x-axis, so in the Fourier plane, it will be expand in the x-axis. Sorry, here it is squeezed in y-axis, so it will be expand in the x-axis. Okay, let me repeat it again. So classical squeeze light field, if we consider a light which is squeezed about y-axis, so in Fourier plane, it will be expand in the y-axis. So similar to this. Okay. So in quantum mechanics, we squeeze in phase space. In quantum mechanics, we squeeze in phase space Q and P. But here in classical, we squeeze in real space, X, Y, and Fourier space. f of x, f of y. So we will now look closely to the system we see. These two worlds share same mathematical language, but how? So we saw that the probability, amplitude in quantum mechanical or quantum mechanics behave similar to that of the amplitude of classical field. Okay, so here where the magic begins. So when Maxwell equation is under the paraxial approximation, it behaves mathematically identical to that of equation governing the quantized light. So we can say that the paraxial approximation behave as a bridge to Maxwell equation to the quantum mechanical equation, or we can say as Schrodinger equation. Okay, fine. Now let's assume there is a state n comma m where n tells us about the number of photon, or we can say n number of photon in mode 1 and m number of photons in mode 2. Okay, these satisfy the quantum harmonic oscillation equation. If so, we can write h nm is equals to e nm nm, where h is the Hamiltonian of the harmonic oscillator and enm is the eigenvalue for different modes. Fine. If on the other hand, the paraxial equation, it is harmonic oscillator equation. On the other hand, paraxial equation or paraxial wave equation takes strikingly similar form like HSL, where SL stands for structured light, UNM, theta, eta is equals to CNM, UNM, theta, eta, where HSL is the Hamiltonian of the structure light, and CNM is nothing but the classical eigenvalue. Okay, and UNM, zeta, eta are the Hermite Gaussian modes. Okay, and zeta, eta are the normalized spatial variable. Normalized spatial variable, which is equals to root 2 x by omega, and eta equals to root 2 y by omega. Okay, so we can say that each quantum state nm can map with UNM. So, and they both are infinite dimensional orthogonal basis in their respective spaces, and any quantum continuous state which is superposition of nm has a structured light analog. They have a superposition of UNM in the classical analog. Okay, and so the last is for classical analogy, when a classical light, which is assume a circular polarized light is focused by a cylindrical lens. Cylindrical lens. So what happen is when it is focused by a cylindrical lens, it only focus in one dimensional. So one dimensional focus is nothing but it gets squeezed in one dimensional and it is unhampered in the other. So we get a squeezed classical light.
So we are going to establish a relation between quantum squeezed light and classical squeezed light. Even with the best classical light sources and measurement techniques, there will always be a certain level of noise that we can't eliminate due to quantum nature of light, which we call as SQL, standard quantum limit. So this limit applies regardless of complexity of the optical system, whether we are dealing with a simple single beam of light or complex arrangement of multiple beams and detector. So the SQL remains a constant. It's a fact. So let us take an example of quantum squeezing. Modes are defined by the quadratures, canonical variables or quadratures Q1 and Q2. So if these modes are in a vacuum state, we denote this by 0, 0 state. So this is the lowest energy state of the optical mode. The simultaneous measurement of two quadratures Q1 and Q2 follows an isotropic Gaussian distribution, which we all are familiar with. Or if not, then we will derive this in the later sections. 1 by root pi exponential minus q1 square upon 2 minus q2 square by 2. So the probability distribution will be the mode of this wave function. So now we are going to so I have drawn up image in which there is a probability distribution uh, uh, that states probability density distribution in the states q1 and q2, and this one is the probability density distribution in the basis q1 and q2, and this one is distribution as a function of polar angle theta. So here theta will be tan inverse uh, q1 by q2. So for vacuum state, q1 and q2 ratio is 1. So we can clearly notice here the theta uh, for so what we can observe here is the ratio of q1 and q2 is same. So uh, no matter what the angle is, but the q2 or q1, any of the quadrature remains constant as the function of theta. So now a two-mode squeezed vacuum state can be generated by applying squeezed uh, operator to the vacuum state. Squeezed operator is S, a function of tau. So this is the squeezed operator S function of tau is defined as exponential of minus tau A1 dagger A2 dagger uh, plus tau conjugate A1 and A2. So when we apply just a quick algebra, uh, when we apply A1 and A2 on Nm to a number state n and m, so this will give us nm, n minus m, n minus 1 and m minus 1. And again, creation operator when applied on a number state, this will give us n plus 1 and m plus 1, and the state will be upscaled. So in short, the tau state, which we defined as the quantum squeezed state, will be finally equal to 1 upon cos of hyperbolic r sigma n equal to 0 to infinity exponential minus iota theta tan of hyperbolic tau upon n and m m sorry n n n. So this is tau cos of, yeah. So uh, this can be obtained, this state can be obtained by using Lie algebra. So this proof is given in detail uh, in the project report. So deriving this will take much longer time, so I'm skipping it. And from relations which we know in between the number state and the uh, state of quadratures, state as a function of quadratures. So from this relation we can obtain the squeezed state psi s as 1 upon root pi exponential minus of q1 plus q2 square upon 4r square, this is q2, sorry, minus r square q1 minus q2 upon 4. So r here is exponential tau mode. So tau is the squeezing factor, and it depends upon the tau, how much the light is squeezed. So now this can also be proved using Hermite polynomials, Hermite Gauss functions. So this derivation is also given in the report, so I'm skipping it and coming to the topic. Uh, so again, looking at this figure, the quantum squeezed vacuum state tau overturns the standard quantum limit SQL, which we defined earlier. So noise is here we can see that noise is redistributed, but it's not eliminated in any of the quadratures. So with varying polar angle theta, the noise oscillates between these two extreme values, which we can observe in this figure. As we define theta is equal to arctan q1 by q2 here. So in this case q1 is much larger. So let let's say q1 is q1 tends to infinity and q2 tends to 0, then this term will become tan inverse of infinite, so which is pi by 2. So at theta equal to pi by 2, this seems to be a Gaussian curve, and for the other angles this seems to be a very low valued function. Now we will do classical squeezing in context to structured light. This is an analogy with quantum squeezing. So the ladder operator, this is classical squeezing. The ladder operator remains almost the same. Only the difference is that uh, this and this will be defined as will be denoted by these symbols, and when operated on the states, the results will remain same as that was in the quantum case. So the classical analogy of the squeezing operator is almost same minus tau a1 dagger a2 dagger plus tau conjugate a1 and a2, which we defined earlier. The fundamental Hg mode, which is 0 0, which is analogous to the quantum vacuum state, is transformed by squeezing operator as function of tau to generate a classical squeeze state, which we denote as u of tau equal to s, a function of tau, applying on the state classical vacuum state. So the squeezed state can be expressed uh, by the similar expression which we used to express in quantum state. So the coefficients are also borrowed here from the quantum squeeze light. So Cn is equal to 1 upon cos of hyperbolic r. The classical squeeze structural light inherits properties from quantum squeezing, such as correlation between modes and noise redistribution. So these properties are explored both theoretically and experimentally in the later sections, which we will be describing. So the fundamental Hg modes U00 is the classical counterpart of quantum vacuum state 00, and the modes intensity profiles are can be shown, and which we have in the research paper. So I would like to draw that picture here. So now the mode intensity profiles can be seen here. So these are at different propagation distances, z equal to 0, z equal to r, which is Rayleigh range, and z equal to 5 times of zr. So here the beam waist wz, we can see here wz here. So the beam waist shown as this counterpart, this one, defines the diffraction limit for the fundamental modes, analogous to a standard quantum limit in quantum optics. So this is the propagation. This is a 3D uh, projection, including the propagation distance, propagation length, along with the uh, propagation of light. So here we can see the coordinates are scaled by beam waist wz to emphasize the universal shape of the mode, which we can see is a circular here. The beam waist can expand along propagation z during due to this diffraction, and following the standard Gaussian beam evolution. And this beam waist, yes, the beam waist is defined as omega naught 1 plus z upon zr. Zr is Rayleigh range, as we mentioned here. So So what we observe here is the circular symmetry of the fundamental mode is preserved during the propagation with no directional preference. The classical squeeze light structure is squeeze light uh, U tau exhibit an elliptical beam waist indicating asymmetry in x and y directions. So but in case of when we apply classical squeezing, when we observe classical squeeze light, the reduced waist size in one direction means the classical squeeze light surpasses the diffraction limit. So here we can observe this is the WZ, the waist beam size, but it surpasses the diffraction limit, which is standard. This white one is the standard spatial limit for both the directions, but one of these directions surpasses this limit. So this squeezed state exhibit an elliptical profile that rotates and oscillates during propagation, as we can observe in this propagation figure. The direction of squeezing periodically flips, mirror the phase evolution uh, of quantum squeeze light, which mirrors the phase evolution of the quantum squeeze light. So the theta evolution, the theta can be observed here. We can define tau as tau exponential iota theta, or we can write it as e iota theta, r e iota theta. So the theta evolution is tied to squeeze parameter, which is tau, where tau is the squeezing strength and theta governs the orientation of the squeezing in xy plane. So theta in quantum optics, we know that theta behaves as theta as a function of z propagating direction, theta naught plus 2kz. So it is oscillating, it leads to a periodic oscillation. So what we observe here is this classical system inherits its behavior. So that is what the motto of this topic is.
Of classically squeezed light. So before, like we already know that we are here treating a structured light as an analog of the quantum squeeze light. So we are just looking at how this squeeze light, classically squeezed light, is generated and detected, so that we can get to know how light gets squeezed. So we'll first look at the experimental setup of how these things are working. So here in this figure, you can see that the light, quantum light, how quantum squeeze states are generated in the above top figures and detected. So in figure A, you can see the generation of the quantum squeeze states, and in the C part, you can see the detection using polarizing beam splitter. Uh, Given that the same analogy that we apply in classically squeeze light, we can generate a classically squeeze light by sending high energy by sending a pumped laser through SLM. SLM is also known as the spatial light modulator. So I will explain the working of it in a moment. So we'll first see how this functions. So the pump is actually a laser which shoots photons into the SLM, and the single high energy photons are then breaking the pair of uh, low energy entangled photons. But this photons, a single photon is breaking into two photons, right? So the higher energy, the higher corresponds to the higher frequency photon is known as the the signal photon, and the other one is known as the idler photon. And and this is how the generation of the quantum squeeze light is done in the quantum light. And then how we detect the quantum light, how we detect the quantum squeeze light. So we passed it through a beam splitter, and then we look at the probability distribution of which detector lies the first. Then we get to know that which light is which in which direction the light is squeezed. So now we look at its classical analog. So the main components of the generation are laser source, SLM1, which is spatial light modulator, are the main and filter are the main. These three, sorry, just yeah, these three, one, two, and three are the main of the classical squeeze light. Propagate the lens setup, and the lens setup is the propagation part of the experimentation. While on the other hand, in detection, the SLM2, Fourier lens, and CCD are included in the detection part. So we'll first look at how spatial light modulator works. So spatial light modulator is actually classically squeezed light is a superposition of all the Hermite Gaussian modes in a given diffraction order. The important thing to note here is that the order and the modes are different terms, so do not miss them. So how this SLM generates a classically squeezed light? So it has a mask function which is given by the following formula: exponential iota u1 minus 1 c a of xy sine of pxy plus 2 pi uxx plus vyy. So this mask function is behaves in such a way that it actually adds a phase, incoming phase to a field, right? This phase, then after adding this phase, we generate the Fourier transform of the light, which is, please excuse me for a moment. Yeah. Which is given by, which is given by summation on n Cn un of n. Here, Cn is given by, we already know, tan hyperbolic to the power n tau upon under root cos hyperbolic of tau. So this mass function is encoded in such a way that it maximizes the number of modes in Cn plus 1 diffraction order. Diffraction order, right? So all the modes are concentrated in the Cn plus 1 diffraction order, and that's how we get a squeeze light. Now coming to the SLM2. So SLM2 is encoded with all the conjugate terms of un comma n. So what will it do? So it will actually decompose all the modes that are present in the first order diffraction. Before coming to SLM2, there is one thing which is called as a filter. So what filter will do? So filter will filter out all the other modes except the plus one, all the other orders except the first diffraction order, right? So after going through filter, only one diffraction order remains, and then it passes to the SLM2. SLM2 then decomposes this first order diffraction into its components, and lens set up after the SLM2 then converts the real space into Fourier space, and in CCD we capture the image, and then we get to know how the light is squeezed. So this is actually the basic working of how we do classically squeeze light. Thank you.
Squeezed light in real space. So I will explain two sections, one in real space, one in Fourier space. Okay, so for real space, we will conduct two experiments, two experimental sets. First with SLM1, or second with SLM1 and 2, both. In SLM1, what we do, we will start for SLM1. So SLM1, we will take in 148 nanometer wavelength laser, and after that we will deflect it to a SLM1. So SLM1 working is explained by earlier, so I will not explain that. But after that SLM1, I will use a lens to focus my light. So what's happening here? I have a laser source. It's going to SLM1. It's going to our lens, something like that. It will focus at focal point. It's the focal plane. Okay, so at focal plane, because of SLM, I will get my squeeze state, something like this. So it's squeezed in one direction. So my lens is working at SSL limit, standard special limit. In SSL limit, it focus at focal point. It just gets minimum. It will get it to its minimum waste, which is standard special limit. But because we have used SLM1, the our light will get squeezed in one direction, so we will surpass the SSL limit, and in one direction the light is squeezed more than SSL limit. So as explained earlier, in SLM1, here we are considering 11 modes of SG, Hermite Gaussian. Now it's the lowest modes, and the upper modes are negligible because their coefficient are going to zero. After that, so for recording, we use CCD camera in transverse direction. So we will put CCD camera at different position to record different images. So after that, our experimental result tells us that at z equal to 0, we will get squeeze state like this, and at z equal to 5 ZR and z equal to plus 5 ZR. ZR is the Rayleigh range, which tells us which like the distance at which our intensity becomes half. So you can see, like here it's minimum, and something like that. Here is 5 minus 5 ZR, it's plus 5 ZR, something like that. So I can show you the figure. So here two things are happening. At z equal to 0, there is squeezing happening in the one this direction, and it's expanding in this direction. But at minus 5 ZR, or phase is evolving with time, so I will get these type of states. So as in quantum light, we can take the analogy. If my light is like this, quantum light, squeeze light, but this is alpha 1 quadrature, this is alpha 2. As it involves, as like something like that, get like this. Now, uh, okay, so second thing I explained earlier is the waste is increasing as we go to increasing ZR or minus ZR, Z distance. Now the other thing is our beam profile. Like in quantum analogy, you have seen that if I have something like that structure, if I plot it, if I plot, sorry, if I take this quadrature, if I plot alpha 2, so it goes something like that. It will like pi by 2 maximize, and 3 by pi by 2. It will get maximized. Same is happening here. So what we will do? We will take, we will measure, normalize radial size, which is something like that. I am denoting it with some Rg divided by omega g. So what is Rg? It's the beam waist, or I can say beam size at z equal to 0 in at maximum squeezing, in direction of maximum squeezing. And what is omega g? Omega g is the fundamental Hg mode waist. So I am dividing it by it because of to normalize our coefficient. So as I progress from z equal to 0, this is the focal plane, and if I go in this direction, what is my mine is 5 zr direction. The first it's the SSL limit, breaking the SSL limit. After that, it will get constant because we have normalized it. Same like this. So now we will move to our measurement set 2 and set 2. So in measurement set 2, we will use SLM2 also. As explained earlier, we will observe the spectrum of classical squeeze structured light. So after taking the experimental data, what we will get that we will maximally get the contribution from these three modes, U11 and U22. So why it's happening here? Why these three modes? Why diagonal modes? So first thing is bidiagonal modes, because SLM1 is directly conjugate of SLM2. It's like working of conjugate type. So if I take the inner product, I will get only diagonal terms. The other terms will be cancelled out. And the second thing is I can take quantum analogy. In quantum analogy, if I have to get squeeze state, what I can do? I can operate squeezed operator at my 0 day state. This is the vacuum state with two modes. Vacuum state. Now, what is S2? It is the exponential zeta A1 dagger A2 dagger minus zeta star A1 A2. Now, if you try to do, if you try to expand this term, I will get something power 2, power 3, something like that. So I will, if A1 is increasing by 1 photon, it will also increase by 1 photon. So I will always get diagonal terms. So my squeeze state is combination of these diagonal terms. Then now the second thing is why I'm getting only first 3 or 4 terms, because as explained earlier, Cn value has some coefficient 10 hyperbolic tau raised to n. As n increases, the tau values we have taken 0.78, something like that. So for 0.78, the 10 hyperbolic value is 0.65. So if I take power something 2, 4, 5, it will get decreased. So we can neglect higher Cn terms. And other factors also, there has cos hyperbolic terms, and that will also contribute to Cn factor. So we are ignoring these terms. So this is the main thing about or classical squeezing in real space. Now I will talk about classical squeezing in Fourier space. So first I can also show you one diagram. Yes, this diagram. So in this diagram there is n and m. These are two modes. As n and m modes are increasing, it will only contribute to diagonal terms. The other terms are neglected. Now we are coming to Fourier space. So I can give some insight about Fourier space. What is Fourier space? So if I have some beam, like if I have some light, it is deflected to some open to some we can say aperture. After that, if I have lens, so it will focus my light at focal point. But if it is diffracted at different order, my light will get focused at focal plane but at different points. So the minimum point, the center point, it called spatial lower spatial frequency. These are points of lower spatial frequency. And the higher order terms, these are higher spatial frequencies. These frequencies depends on the direction in focal plane. Now, what's happening? If I have some beam, it has some equation. The lens will add some parametric term. So I can say a paraxial some terms x square plus y square exponential term. So after that, we will get form of Fourier transformation type, and it's the our real coordinate is changing from real to spatial frequency coordinate. Now here we are using 4-up setup. In 4-up setup, I have two lenses. Or light is coming like that. We'll get this is our focal plane. It's the Fourier transformation plane. After that, we get reflected. At second lens, we will do inverse Fourier transformation, and we will get our real space. So what's the benefit of this thing? So at focal point, we can remove or higher spatial frequencies or lower spatial frequencies by adding a filter, something like that. If I applying this filter, it will just pass the lower spatial frequencies and block the higher spatial frequencies. Okay, so if I want to consider only +1 diffraction order, so I can use this type of filter. Now the second thing is we are doing tight focusing. For our west, so that if my phase is changing very slowly, but from the change of phase, the reflection of that in spatial frequencies will be high. We will see the same reflection as earlier. So the main funda is in Fourier transformation, I will get something like that. If in real transformation, if I have x or y, this is like x, this is like y. If my beam is like this, but in Fourier plane, it will just get inverted. This is fx, this is fy. So all the terms it's coming from higher frequencies, lower frequencies. The terms are coming from higher frequencies because the higher diffraction order. Now we will also use here CCD camera and measure the intensity. So after measuring the intensity, the main thing we will see, is full width half maxima. It's the diagonal direction, which is this direction, and plot of intensity. Okay, now at full width half maxima, this is full width and half maxima, we can see at Gaussian, and there is squeezed and there is quadrature. At Gaussian, it's the fundamental HG mode, so it is as standard spatial limit, which is giving us 0.27 lambda west. Now at squeezing, we are breaking this limit, or we will get 0.87 lambda. Now the consequences of this squeezing at the orthogonal direction, what we will get? We will get 2.60 lambda as the orthogonal direction because of this squeezing happening in one direction. Now this is our experimental result, but in our simulation result, we are getting something like 0.60 lambda. It is breaking our diffraction limit, like near diffraction limit. Diffraction limit, I can explain this, don't get confusing SSL limit and diffraction limit. So diffraction limit is the resolution limit of image system. Like we are using numerical aperture to tight focus our beam. So it has some to NA. NA value is something, just 1 second. I think 0.97 maybe, something like that. So from this we are getting 0.5 lambda. So it's the near diffraction order limit. SSL limit is how tight you can focus your beam. So this limit is we can do by lens or something like that. We can focus our beam. This is the standard special limit, and diffraction limit is different. So the main thing is how can we overcome this diffraction limit? So experimentally, we have to involve or incorporate higher order eigenmodes. Which is beyond this paper scope. So now we have super oscillatory structure of classical structure light, which is explained, which is the other person will explain.
Structure of classical squeezed light. So before we proceed to understand the super oscillatory structure, I will like to introduce a term called local wave number. Local wave number is nothing but the gradient of phase. Okay, so in tightly focused classical squeezed light, we have some local wave numbers which is greater than the free space wave number. We know free space is equals to free space wave number is equals to 2 pi upon lambda. So at some positions these local wave numbers are greater than free space wave number. Okay, so and we all know in classic in standard diffraction theory the local wave number does not exceed the value of free space wave number. So here we have super oscillatory nature, right? And this super oscillatory nature or super oscillatory structure is nothing but the consequences of tight focusing. As earlier explained, the concept of the tight focusing, we want to reduce the wedge size, and during this we come across this super oscillatory nature. Now we will proceed to the discussion section. In this section, I will completely summarize what we have done in this experiment or in this paper. In quantum optics, we squeeze states. Sorry. In quantum optics, squeezed states are made by using squeezing operators. On the vacuum state, like we have a vacuum state, and we operate a squeezing operator. We get a squeezed state, right? Or in this process, in one direction we lower the noise, and consequently in other direction we get higher noise. Like we have a vacuum state, if we operate a squeezing operator, we get squeezed along this direction, squeezing along this direction, but we we get larger noise along the other direction, or I can say perpendicular direction. Okay, this behavior. So now we are already seen in paramagnetic. Uh, we are already seen in down conversion process that we have a photon of frequency omega p, and we get two photons of frequency omega naught. Despite the fact that we are having more number of photons, we get uh, squeezing along that direction. Okay, this behavior helps to beat the standard quantum limit, which is useful in area like gravitational waves, wave detection, and quantum imaging. Instead, uh, and in now if we talk about the classical classical case. In classical case, we have used SLMs. SLM. What is SLM? Spatial light modulators, like to shape the light. They they create what? Sorry, you. So initially, to create classical squeezed light, we combine Hermite Gaussian modes. Here, the basic Hermite Gaussian modes acts like a vacuum state in quantum optics. Okay. The resulting beam has elliptical shape. Like when we combine the higher order, higher order Hermite Gaussian modes, we get elliptical light. Just like in quantum case, when we operate squeezing operator, we get squeezed light. Here we are combining higher order Hermite Gaussian modes, and we are getting this elliptical shaped light. Okay, so the resulting beam has elliptical shape. Its width is reduced along the squeezing direction, like same as quantum case. We get a uh, we, reduced width along this direction and expanded width along this direction. Okay, in this, so this is very similar to the case of quantum. Like just the difference is we are dealing there with quantum noise, and here we are dealing with the width. Okay, both in experimental and simulations shows that the squeezed beam can have a spot size that is smaller than standard Gaussian beam. Okay. Um, Experimentally, the spot size, as we are using tight focusing, experimentally the spot size reaches to 0.87 times the wavelength. And if we talk about the simulations, if the simulations says that it can reach lower value up to 0.6 times the wavelength. But the consequence is that the beam gets wider in the other direction, just like in quantum case. A key point of study in the squeezing effect stays strong even when the beam is tightly focused. When when focused the high numerical aperture microscope, just which is tight focusing, the focal wavelength measures as gradient of the phase, as I explained in case of super oscillation, super oscillatory structure. The gradient of phase goes beyond the normal phase space value, which is 2 pi upon l, sorry, 2 pi upon lambda. This lead to deep sub wavelength super oscillatory behavior. Okay, as I explained earlier, this when kl is greater than k, which is 2 pi upon lambda, this lead to super oscillatory behavior. Okay, now we can see in this image that the blue lines, these are phase, and the red one is gradient of the phase. In most of the space, the red line lies below the blue line, but in some instances, like this, at this point and at this point, not sorry, at this point, we are getting the gradient greater than the phase space value. Okay, now if we just zoom this portion, what we actually get is that it is it. Now the blue one is again experimental and red one is simulation. In experimental, the full width at half maximum is about 7 lambda divided by 100. While if we talk about the full width at half maximum in simulation, we get lambda upon 1000. Okay, so for this case, we are getting lambda divided by 1000. Why this difference? As we are using CCD for the detection, CCD has its resolution limit. Due to that resolution limit, we are getting some uh, wider value of full width at half maximum. Okay, now for squeezing, just like in quantum case, we have squeezing parameter. Using that squeezing parameter, we can tune two things. What are they? First is we have squeezing parameter tau. Using this, we can tune two things. First one is spot size. Okay, and the second one is stiffness of the gradient. Okay. And using these two parameters, we can control features of light very precisely. Okay, so the in this paper the study also this paper also measured the model spectrum of squeezed light. It shows that the diagonal structure similar to that of diagonal structure similar to that of found in quantum squeezed state. Just like we found in quantum squeezed state that only diagonal elements contribute. Here too, we are getting we get using SLM the experiment. It's already explained by Vikram that we already only get the diagonal contributions, not the non-diagonal contributions. So this is very much similar to the quantum case. Okay, so it is our primary motto to find the classical analog of quantum squeezing, and using this experiment we found the classical analog of quantum squeezing. Thank you.